Okay, good afternoon, everyone. Welcome to the lecture number 12 on augmentation systems. And this is perfectly synchronized with what we have here this morning with our last external speaker from United. This is the outline of the presentation. You have to admit people also. Too many things. Okay, leave it like this. This is okay. So this is the outline of the presentation, and that we will talk about. We will introduce what it is.
That's just because if you want to pass, you need to change your screen to PowerPoint. I think you will not work here. Understand?
Yeah. Okay. Then we will talk about the two ways of augmenting the system: ground-based augmentation system and satellite-based augmentation system. So, what is augmentation? In this slide, we can have the main ideas about what augmentation, the signals that are used nowadays in our GPS are not enough for certain users. So we need to augment, we need to improve those signals and services. We will be talking about 3 or 4 different concepts that I will define: integrity, accuracy, availability, and continuity. We will see that they are different, but they are all together related. As we can see, there are 3 different means, 3 different procedures to augment the current systems that are the satellite-based augmentation systems. We will see, like the example we saw earlier this morning with EGNOS. We have also the possibility to do it by ground, by deploying an infrastructure at an airport and then serve the surroundings of the airport. Or we can do it autonomously. We can do it based on the aircraft. That is called ABAS, aircraft-based augmentation system. Okay, as I said, there are certain groups of users that require a more accurate solution with integrity, with very high level of continuity, and with very, very high level of availability. Those primary group of users is the is the civil aviation users. They are lots of airplanes that are using GNSS, and they require very demanding performances, as we will see. But also there are other segments, like for example, the maritime applications or ground craft applications that also require augmentation, or that could also benefit of this augmented system. For example, the logistics or the transport and so on. Okay, first definition, the accuracy. What is the accuracy? The accuracy, as you can read in the title, is the difference between the measured position and the actual position, what we call the ground truth. If we know where are we and we are computing the position at any other point, we can compute the difference in coordinates. And this is what we call the error, or the accuracy, and we can say it in the both ways. Here, this picture, we already saw it last week when we were talking about this particular day, 2nd of May 2000, in which the select availability was disconnected. Before, we already saw that the user performance, the accuracy was very degraded, because the intentional degradation of primary clocks, also orbits, but the clocks were driving the error in vertical and horizontal in different colors to something that we cannot use the system for flying. with errors of plus minus 100, 100 something errors. This is not acceptable error. We see clearly this event in which the select availability was disconnected from the satellites, and then we can see the accuracy, the nominal accuracy that we have since then. Around 4 meters of vertical accuracy, 95% of the time. The accuracy is good, but we will see that we can further improve. Integrity, second definition, integrity. As you can read, this is the ability of the system, the navigation system. Any means that you are flying, that you are doing the approach, whatever you are doing, this system, to provide timely warnings to users. And so if there is a problem, the system must notify the user and must shut it down, must abort the operation, for instance, when it's not safe, when it should not be used for navigation. And this is an important point. GPS, GLONASS, Galileo, all of the Genesis constellations, as they are on their own, they do not guarantee the integrity. They are not integer, meaning that if there is a problem, if there is a failure, it can take a lot of time. And you can see that it's minutes or hours even to notify a failure. For example, we can see, we will see later in the talk, a real failure of a clock, of a satellite clock, one of the atomic orbiting clocks inside the GPS satellite, and then it can take a lot of time to detect this error. Of course, if we are landing, and the landing will take a few minutes, we need a very short, what we call the time to alarm. And we need seconds of time to alarm. We cannot be waiting up to 16 or 2 hours. This is not acceptable. Continuity, another definition, that is the availability of the system to function without interruption. So imagine that we are landing an airplane, and we know that it will take about 150 seconds, few minutes. Then we must assure, or we have to make the landing continuously, without interruptions, without stop. And then we have the availability. The availability is a numerical metric, a numerical number that tells us what is the fraction of time in which all of the three metrics, accuracy, integrity, and continuity, are under the requirements, are completing the requirements. And so you can see them, they are tied, the integrity, the continuity, and the accuracy with the availability. Here you can see the numbers. So for the continuity requirement, we need 10 to the minus 5. So 1 every 100,000, 1 epoch, or 1 second every 100,000. This is the probability of aborting the procedure, for example, the landing. And for the availability, we will see that requirement is very, very high. More than 99%. We will see how many nines we have to perform this, that the system must be working. So here we have the big picture. We have the big picture of the augmentation systems. We have our aircraft flying. The pilot, the crew, they don't know where they are located, but they have to follow. They have to follow a given path, a given landing slope, a given route, whatever. There will be an error. For sure, there will be an error. This is something we have to live on. But we have to control, we have to bound this error. We have to control the size of this error. And then this error, you can see it in red, must be bounded, must be inside this blue circle, this other region. So it must be contained inside here. And then this is what we call, later we will see, the protection levels, meaning that the error of this aircraft, where we have people inside, we have safety of life, must be protected within this blue circle. Then we will see how these circles they get higher, they get larger or smaller. We will see it later. And then when these confidence bounds get too big, and too big means that they are larger than this other limit, we will see how the system becomes unavailable. Okay, and here we have another requirement. We will see numerical requirements here and there. And for example, the probability that the error, the navigation system error, this is what it means NSE, that is out of this protection, out of the protection circle is 10 to the minus 7. So it can happen, but the probability is very small. It's 1 in 10 million. So it's something very, very rare. Okay, so and the time to alarm, is around 6 seconds. We will see later a table with all of these values. Okay, let's see what events can happen. And maybe now you are curious to see what can go wrong using GNSS. So here we have some different faults from that we call fear events. So events that pose a risk on the system, and we have these categories. And we can have a ephemeris error. Yes, but the orbital parameters that we were discussing last week, they are not accurate. And then you can see that this can happen with this probability. We can see problems on the onboard clocks, on this onboard atomic oscillator, or problems on the signal, or on the bias, or the code carrier divergence. We can see, and there is a lot of studies going on trying to categorize the probability of such failures. For example, we can see the erroneous GPS ephemeris. Then we have this description, and then these probabilities. For example, 10 to the minus 4. This is the probability per hour per space vehicle, and this is the probability of this failure. Here we have an example of a failure happened the 1st of January 2004. So everyone was celebrating the new year of 2004, and then one of the orbiting satellites at 6:30 UTC, so it was a holiday, and during the afternoon of those holidays, one of these satellites, the clock, had a problem. And then there was, we will see in the next slide, we will see the value of these satellite clock going very out of tolerance with a big error. So there is always people at the GPS or Galileo at the control segments. There are always people, but they took some time to detect the failure, to confirm the failure, and to start issuing warnings about this satellite. In particular, there were almost 3 hours of delay between the failure and the first warning. So you can see that this is something real, and this happens. The probability is small, but failures happen from time to time. And so we will see how this affects. Okay, this is this particular event. We can see the clock. Typically, these clocks are very stable, and here we can see this enormous drift. You can see the meters. We can see the very big bias with respect to the GPS stuff. And then we can see that it took almost 3 hours, 2 hours, 3/4 to set it unhealthy. This means that for 2 hours, 45 minutes, every receiver that was tracking this satellite was not aware of this satellite having this problem. And this poses a very big risk, especially when you are flying low, when you are approaching a runway at the airport. Okay, these are the big pictures that we will discuss during today's talk. And here are the different phases of flight. So we can have very loose phases, like for example, when we are in the middle of the ocean, when we are in cruise, when we are in route. Then we have when we have in a congested area, like for example, when we are approaching or departing from an airport, and the most difficult part of the problem, when we are expecting more and more from these systems, is when we are at the airport. When we are approaching the runway, like we saw this morning, or when we are even on the surface, when we are taxiing from the runway to the terminal building, or from the terminal building to the runway. There, under conditions of fog, or storm, or whatever, is where we are demanding more. These are the requirements. These are the requirements stated by ICAO. ICAO is the International Civil Aviation Organization that dictates those requirements, no matter if we are using GNSS, if we are using whatever other means of navigation. And here we have the two metrics of accuracy in the horizontal and on the vertical plane. We can see the different phases, and then we see the integrity required for this navigation phase. We see the time to alert, the continuity and availability, all of the metrics I was introducing before. And we can see for this LPV 200, that is the most demanding phase, we can see that we have meters, we have few meters of accuracy, we have 6 seconds of time to alert, and we have this very high availability requirement. And you can see the famous 5 nines. Everyone that talks about SBAS, they are very concerned about these 5 nines. So 99.999% of the time, the system must be working fine. Okay, we will see how we can manage, how we can reach this level of performance. And basically, we will be talking about GBAS and SBAS. And first, we will talk about the ground-based augmentation system, and later we will complement it with SBAS. And in this slide, you can see how we tackle, how we remove different error components, different errors that we have on the signal. Like the lecture we were seeing earlier this morning, that we have different models. We have errors in the satellite clocks, we have errors in the satellite orbits, in the propagation channel, both at the iono and at the troposphere, and we have errors at the receiver side of the Genesis jet. So we have different techniques, and you can see that GBAS uses common differences, and we will see it in a minute what this means. So most of these terms are removed when we are differentiating the measurements from one satellite seen by a civil airplane at a nearby reference station, and we can see SBAS. And SBAS uses a different approach to mitigate those errors. This means that because we are covering a big country, we are covering a continent, well, we need to approach the problem with a more wide, a more bigger, broader sense. And in both cases, then I'm done with this slide, is the multipath and receiver noise that Professor Jama was explaining earlier this morning. Both are mitigated with carrier smooth filter. Okay, so let's see the first system, the first augmentation system, the GBAS. We can see the main ideas here. We are approaching a runway with an airplane, and what we will do is that we will cancel most of the errors because those two receivers are not very far away, are within 40, 50 kilometers, one about one goal. And this is because we are sending information, and this message is being broadcast by a UHF link from the ground station to the airplane. And so we cannot go very far away. So this is the idea. We have to deploy a ground infrastructure. First idea. So within the airport, we are at a civil airport facility, we have to install what we call a reference station. A reference station is some antennas, and it's a hardware, like we saw this morning in Malaga, in the Spanish airport, that was shown by Javier from Enaire, with redundancy. We have more than one antenna, typically 4, and 4 associated receivers. So they are deployed in a secure area, and we can, they are in a safe place. So by taking measurements from these antennas and these receivers, we can process it, and we will see how, and we can broadcast these corrections to a nearby user, a nearby civil airplane approaching the runway. This piece of hardware and software is the ultimate responsible for detecting anomalies. We are trusting the civil plane that is approaching the runway is trusting all of the procedures that are performed into the reference station. So there will be some change about the health of the satellites, about the measurements, and we will see how this works in practice inside the reference station. And then we receive the data, and the data looks okay, we have the confirmation that we can use it, then we will be approaching the runway with very high accuracy, integrity, continuity, and availability. Remember, always the four metrics. Okay, so the first idea is redundant reference receivers. If one of the receivers or antennas is down for maintenance or is hit or whatever, the GBAS has redundancy, and the GBAS station has redundancy, so we will be operating with the three other receivers and antennas. So it is something that it is perfectly fine. So the GBAS station is the one generating the differential correction. We will see it now. And these corrections, the correction, let's say, with that is correcting every satellite that we are observing, it is broadcast by a radio link, by a VHF channel, a very high frequency radio channel, and because of the limitations of this channel, the range that we can use with the GBAS is around 40 kilometers. This is a limitation of the battery. This is how it works. This is, let's say, the brain of a GBAS station, in which, starting from the left-hand side with the antennas, we have, as we said, multiple antennas with multiple receivers, and then we perform, we check the signal, the SQMs, that are the signal quality monitoring. Then we check the data, so it's not only the signal that we check, it's the content. Then we check the measurements. So we screen faults on the signal, faults on the data, faults on the measurement. So we make everything that looks good. Then we perform a smoothing, as you can see. So we remove the noise and the multipath of the antennas. And then we go to executive monitoring. And executive monitoring is the one that is checking, like, okay, do I see the same errors in one receiver than another, or is one of the receivers or the antennas that is not working fine? We take benefit of the redundancy, and then we have other monitors that are checking the signal, and if everything looks good, if the measurements are correct, then when we encapsulate this information into a radio signal and we broadcast to nearby users. You can see the flow from left to right, and then here we are broadcasting the differential corrections. Even the GBAS station has its own receiver for these corrections. So we are also checking what we are sending. And so not only we are generating the corrections and disseminating them, we are also using these corrections to see that everything is self-consistent, everything is working well. Here we have some examples of the accuracy. This is the horizontal accuracy of a GBAS, of a kind of a GBAS station, something that we could see representative of a GBAS station for the north-south versus west-east. So this is the horizontal plane. So we can see very good accuracy at the level of the 30 centimeters. So very good accuracy. And you can see the vertical accuracy in blue here. We can see with a 95% error of half a meter. And so also we have very good accuracy. And we check, we are not only, remember we have 4 metrics. We have accuracy, but also we have the integrity. And then we have the protection levels. You can see that the error, the actual error, is bounded, is protected by this value, the protection level. So that the errors are small. If we have a drop of satellites, maybe we increase a little bit the error, but always bounded by the detection level. We can see how integer is the system by checking the protection level, let's say this red protection, against the blue, against the error. And we can see how well they are bounded. And you can see that always we have small errors with typically high protection level. Yes, you will see all of the points that have low error, but very well protection level. No points, here there is a diagonal, and you will see no points in this down region. If we have the points here become a problem because there are big errors with low protection levels. And remember that this can happen, but this is very, very unlikely. The probability of this to happen is 10 to the minus 7, 10 to the minus 9. Okay, there is a comment here before we finish with the GBAS. That is, how many GBAS, how many of these stations we need to fill a continent? And this is a question. Okay, this is working very, very nice. But if we want to serve Europe, if we want to serve a very big area, how many? Well, we have to first mention, I already mentioned that the VHF link, it is very limited to 43, 45 kilometers in range. We also have problem of the correlation of the ionosphere, meaning that the conditions we are observing at the airport are not the same, will be different to the conditions seen by the civil airplane. And this will be different. The larger, the farther away we are, the less likely that they will be. Or we have the correlation, like orbits and so on. So the errors will be less likely, will be less similar the farther we have the two receivers, the GBAS station and the approaching airplane. Well, considering these three effects, especially the one of the transmission link, this is the actual killer, we will need about 600 stations, 600 GBAS to cover a continent of the size of Europe. Then you can see the cost of GBAS, the GBAS station with the redundancy, with the nice and very good antennas and the hardware. This is very costly. So it is not affordable to have 600 GBAS stations. So what can we use instead of GBAS? We can use another system that is the SBAS. We can use the satellite-based augmentation systems. Of course, the two are complementary. We can have a satellite-based augmentation system for non-so demanding phases of flight, and when we are getting close to a busy airport, we can then use a GBAS station. And this is how we operate in practice. Okay, let's see the SBAS. This is the SBAS concept. And here you can see that with GEO stations, we will see the example of EGNOS, but this is applicable to all of the augmentation systems. And we will see how do we cover a big land, a big piece of land, right? Like, for example, the continental United States. So the idea that we use is that instead of differentiating the measurements like we do in GBAS, what we do is that we tackle the errors separately. So the clock error is mitigated differently than the orbit error. differently than the Yono error, and so on. And so we remove component by component. These are the SBUS systems, the different SBUS components that are in place. So we can see the Japanese example, the Indian example, the European example, and the American example. Okay. And we will see now a little bit more of information of ECNOS. Although we have had an excellent presentation done by Javier from NIDE, so I will go a little bit quicker on this part. So you can see the main contributors to ECNOS, who makes what, and we will see a map with the area in which ECNOS is operating. And this is the European Civil Aviation Conference area. That is more or less, it follows the European territories. Although in the previous talk, we saw specifically which are the territories that we are covering. And then we can see different footprints of the geostationary satellites that are used to broadcast the corrections. Here we can see a similar picture that what we saw this morning. We can see the RIMS, and the RIMS stations are the Ranging Integrity Monitoring Station. This is the acronym for RIMS, that are distributed in Europe. And we will see a map in the next slide. All of this data it's sent to some centers, these master control centers, that they process and they generate this correction. And then we uplink these corrections with these big antennas to the geostationary satellites that are orbiting the Earth at 40,000 kilometers. And this is the link that, complemented with the GPS information, we are serving all of the users in the continent. And this is not restricted to civil airplanes, but anyone with an SBUS, the ECNOS capable receiver. And this is the flow of information. And this is a very quick processing. They have very little time to process the data, see if all the satellites are performing well. If not, remove a satellite, and so on. It's impressive how this works. These are the RIMS, a map of the RIMS, although we had the most updated information in the previous talk, with some of the locations where we have these RIMS. And this is again the data flow. And you can see the different components. So we are augmenting the GPS satellites or any other satellites that will come in the future. We have been introduced about the multi-constellation SBUS. This is coming. We are augmenting these satellites with some other satellites. And this is what we are doing with SBUS. And for this, we have this loop of information. And so now we are not using a radio link, but we are using a satellite link to disseminate and these corrections. Okay, so this is how the ECNOS ground segment looked like in detail. So we have around 30 something of these RIMS deployed in the European territories. And we can think that the RIMS are the eyes of ECNOS, in the sense that are the ones seeing the satellites, are the ones getting the information from the GPS satellites. Then we have different master control centers. These satellites are the brain of EGNOS. The brain of the SBAS are the one that is checking the data, making the calculations, and assuring the integrity. So this is the brain, where is the actual processing taking place. And then we have the uplink station, the navigation and land air station. And these are the stations that are uplinking the corrections to the geo satellite. And we can think like they are the mouth of ethics. And they are talking to the GPS satellite. Everything is published. All of the SBAS processing has to follow very well detailed examples. And there is an organization, the RTCA, the Radio Technical Commission on Aeronautics, that is publishing this document that is called MOPS, MEMOPS. You can see here the title, the Minimum Operational Performance Standard for GPS Wide Area Augmentation Systems Airborne Equipment. It's a very long title that nobody uses. Everyone knows this document by the MOPS, the RTC MOPS. There are different versions. There were the A, that is this, the one that is here, then evolved to the B, to the C, and so on. And in this document, we have a specification of the message. We have how the message looks like, the message that we receive, the differential corrections. So what are the bits that one can expect? What are the contents and the units, the rates, and so on. Everything is very well detailed in this document. Example, just to give you a taste, we can see the different messages, and this is organized. This is well described in this document. So, for example, if we are receiving the message 18, this is about the ionospheric grid point bus. And so it's telling us which grid points are active or not for the ionospheric correction. If we receive the message 2 and message 3 or the 4 and the 5, we are receiving the clock corrections, what we call the fast correction, and so on. Here we have the different information in the MOPS. Here, I will not go into the details, but also you can see how all of these corrections are used. All of them, we have a lot of identifiers, the issue of data for the clock, the issue of data of the ephemeride, the issue of data of there are, and everything has to match. We need to use the information properly. And how to use this information properly, it's detailed in the MOPS. All of the ionospheric corrections, the clock corrections, and so on are here. But we don't have time to go into the particular details. Other important aspect is the timeouts. We cannot use the information forever. Remember that we are landing an airplane. We are landing an airplane during less than 2 minutes, 2 minutes and a half, 2.5 minutes. So we need to be very quick. So, for example, this is the whatever correction we are using, and we have to take into account for a system latency. And it takes a small but not negligible time for all the information to go through the system. Then we have the 1 second, these messages typically last 1 second, that is the time of applicability. Okay? So this is the time where we can use the correction. But what happens if we miss one message or we are busy doing something else? We have some time after the reception of this message in which we can keep using this information. Okay? This gives us a little bit of room to keep using the correction until there is a moment in which the correction times out. And we cannot use later than even time this information. And here we have for the different components, and we can have when are the messages in which we can retrieve the information and the typical the maximum update interval that it can be between 6 seconds and 5 minutes. And so everything is quite short. And then we see the timeouts. And you can see that the timeouts for precision approach are shorter and smaller than the timeouts when we are in a more loose way of navigation, into a navigation mode not so stringent. This is the mask, for example, that is telling us which are the satellites, up to 51 satellites. This is the number of slots that we can use. And here you have an example of using the fast corrections. We will not go into the details, and this is you have the slides for using the messages 2 and 5 and also the 24. So here you have an example of how the corrections are generated. And here you can see how do the pseudo-range corrections are built. So we are taking the correction from the system. It is flying through a geostationary satellite, this correction, and we are adding it to our pseudo-range, to the pseudo-range that is collecting our receiver. And then we have also this range rate correction that is computed by differentiating the two previous pseudo-range corrections. And here you can see the model. The model we will see tomorrow. And here we plug the pseudo-range correction given by SVAT. If we have an SVAT capable receiver, we will have access to this pseudo-range correction. Another important aspect that we will devote some time tomorrow is to the confidence bound. And this is the level of trust that we place to the correction. And we can have different trust to a satellite and to another. If we have an older satellite, or we have a satellite that is not very well observed, or the ionosphere, and we have the capability to use different signals, different ways to the different corrections. And this we'll see tomorrow. So now it follows an example of using the ionospheric correction. Like we saw this morning, the current SVATs, they are using ionospheric correction to compensate for the ionospheric delay. In the case of SVATs, we will see now the grid. In the next slide, we have the map, and we will see different spacings for the so-called IGPs, and ionospheric grid points. You can see that depending on the latitude, we can have 5 by 5 or 10 by 10, and we have a different with different spacing. And then in every of these dots, and show it in the map better, in every of these dots, we have the value of the ionospheric vertical delay. And then we have to project from the vertical delay. Well, if the satellite is on top of one of these points, there is no big projection, but generally we see the satellite with some elevation angle. Then we will project to the angle that the elevation that we are seeing the satellite. And so this morning, Jama was showing a picture of the ionospheric points from Barcelona, and then we can map it to this location where they are located the IGPs. Then you can see how this works in a very concentrated way. We correct the pseudo range, and this we will see tomorrow. How do we make the correction? But also we see the sigmas. And so for every pseudo range, tomorrow we will be building the navigation equation system, and then we will use the equation, but also the wave and the NC. And with this, we will build the system, and we will use least squares to solve for the system. I'm advancing a little bit the content of tomorrow, but this is the least square solution in which we are obtaining the solution that minimizes the mean error and the mean square error. And so this is what we are doing when we are using the least squares. We will see tomorrow, don't worry. But because we are also using very good estimations of the uncertainty of each measurement, we can also derive the covariance matrix. And the covariance matrix is the blue circle that is bounding the confidence bound that is bounding the true error. And when we are on an aircraft, we don't know what is our error. We don't know the exact position. But this is telling us how is the circle that contains the true position. And this is what we call the horizontal and vertical protection levels. And we will see tomorrow how we compute these values. Here we will have everything in one slide, and then we multiply, assuming a given probability, for example, 10 to the minus 7, we assume that the errors are zero mean, as they follow a Gaussian distribution. We multiply, we assume that, well, we can have a false alarm rate of 10 to the minus 7, then we have this coefficient, this comes from statistics, and this computes the protection level. And this is how we derive the protection level, and the horizontal protection level is the same, but with a 2D distribution. But as I say, tomorrow we will have a look. And this bounds our error. So you can see this is just to illustrate the complexity, but don't worry, we will not go into the detail. And all of the relations between messages, the timeouts, the degradation factors, you can see all of the flow of information here and here, all of the different bits of information, but this is the idea. And this is the idea, and this is what I want you to remember. We have the error. For sure we will have the measurements contain an error, the geometry of the satellite is not perfect, and so on. Okay, let's have an error, no problem, but let's assure to the crew, to the pilot, that the error is self-contained, is contained inside this cylinder that we call protection level. And that the protection level is the formula I was showing before. We have a constant that comes from the probability that we expect. Yes, if it's a Gaussian or a Rayleigh distribution, we will have a different K factor. And this comes from statistics, assuming that we have an error. What is the probability of having the error in the tails, the realization of the tails, given a full rate, false alarm. And this comes with a part that comes from the geometry, the range of the different satellites, and a part that comes from the sigmas, from the standard deviations, the confidence bounds. So there is a specific model in the RTCA MOPS document that tells us how to weight the satellites, incorporating the information of the message. So in the message, we will have information about the different satellites. This will give us a protection level. The circle will be, the cylinder will be bigger or smaller. So some results, actual results for EGNOS. Here we can see the vertical error, the vertical solution, like we saw before. So we can see a very good accuracy, vertical accuracy very good, and it is very well bounded. So although the accuracy is less than 1 meter or 1 meter, typically we can see that the bound, the system is very conservative. So we can see that it is very well inside this cylinder we were showing before. Actually, we can see it also with these so-called Stanford plots when we are plotting the protection level, this red protection against the blue, against the error, the actual error. We again see values that are on this side of the diagonal. Small errors, bounded with high, adequate protection levels. And we can see that this has to work in a very big area. We can see the availability examination here for a particular area. So we can fly from the very northern part of Sweden or Norway down to the Canary Islands with using the European vessels. And also for the continuity, remember that the continuity was the probability to perform the intended operation, the approach, without interruption. You can see the continuity range, the continuity metric. Well, this is for some stations, the accuracy for different, for some years ago, what is the measured accuracies in different airports in Europe. And the accuracies, you can see that is in the range of 1 to 2 meters, so it's a very good accuracy. And we are performing examinations continuously. You can go to the ESPD website, which they take care of EGNOS, and they have a real-time monitoring, very, very well done. So let's come back to the actual example that we saw before, these faulty GPS satellites that on Christmas, the first day of the year, on January 1st, had the problems. This is the trajectory of the satellite, what we call the ground path. So basically, the projection of the satellite position on the Earth. And so you can see that it was flying very, very far away from US. It was orbiting very, very distinct part of the US territory. And we will see now the performance of EGNOS. The performance of EGNOS. That also was not inside the coverage area of EGNOS. And remember that ESA ends somewhere here. So it is not in the EGNOS region, but let's see how the system performed. And remember, this was a clock event, so suddenly the clock went out of tolerance and accumulated very big error. And this is how the EGNOS perform. We can see the GPS error. This is the error for different stations. And we can see that without any SBUS, without any augmentation system, we had very large errors, but by applying the corrections, by applying the EGNOS corrections, we had a very nice accuracy. And so it was safe to use the EGNOS solution and the SBUS solution. So this is a working example in which EGNOS was able to detect the fault and protect the user. So if there was any airplane that was approaching the runway, it would proceed nominally with no problems. But without EGNOS, there were hundreds of meters, up to 100 meters of error. So when you are close to the ground, you need to have errors very well controlled. So some references here. I am getting to the end of the presentation. So we have a very nice book on EGNOS with a lot of technical details about how EGNOS was implemented in Europe. And this dissertation, L12 from the Stanford lab, in which they explained very well how a GBAS station was done. So one for SBUS, one for GBAS. So thanks to you a lot for suffering me after lunch. And now we open the time for questions. I don't know, is there any question here on the room?
I have some questions.
Yes, please come close to the microphone.
Take my notes.
Let me see if there is any comment from the remote audience.
Oh. Well, can you talk about the wording alert?
Yeah.
It's after or before you use one model to it makes you this one because 6 seconds before it's a lot of time to.
What we say, or how you need to look this table is if there is any failure.
Yeah.
From the start of the failure until the user gets an alarm, the maximum time it can happen is 6 seconds. So you are landing.
Yeah.
A satellite that you are seeing starts to do something strange, or there is a problem in the signal or whatever. You will start using this satellite. But in 6 seconds, the SBUS or the GBUS or whatever needs to detect the error and say, hey, everyone, don't use satellite 10 or don't use satellite 3. This satellite is not longer usable. This is what the 6 seconds refer to. It's the time to alarm users of a faulty condition. It is very, very tight. If you imagine in 6 seconds, you cannot go to the end. You cannot cross even the building.
Yeah.
And we are using 40 stations, 4 different master control centers. So there is a lot of infrastructure then we are in 6 seconds.
Does this 6 seconds meets the requirement for aerial availability? Or
Yeah. This comes from from the ICAO, from the civil aviation authorities.
I guess that 6 seconds for an airplane.
Yeah,
For me,
it's a lot of
enough
time.
time.
Yeah.
I think that 6 seconds is including the time and the signal goes to the system, and then it invests and then goes up again and again to the maybe 3 seconds is to go down and then up again. So it's
Yeah, because you need to send the correction.
we rate it, send it to the satellite, and satellite back to the aeroplane.
Oh,
So
yeah,
3
got
more
it.
seconds I just to go the round trip.
And to complete the whole chain,
It's
Yeah. It's 2 seconds just to compute the.
When we talk about when I compare the DG, NSS, and SBAS and GBAS, the main difference is on the requirements to follow. That's it. Because you have the same structures and
the requirements do not depend on the implementation.
yeah.
The requirements are fixed
Okay.
by ICAO.
Yeah.
How you achieve the requirement is up to you. Now the airplanes are landing. As
Yeah.
we are speaking, here in the airport, the airplanes are landing.
Okay.
But they use the instrumental landing system. There is another system deploying the aircraft that is complying with this requirement. We do not need satellites. We have been landing planes for 50 or 60 years without airplanes, so without satellites. So those are independent. The requirements are requirements for flight. How you achieve them? It's up to you.
Okay.
If the pilot is looking at the through the window, this is fine.
Yeah.
As long as he or she complies with the requirements.
And the ionosphere delay on the 26 messaging, it's the tech or not?
Yeah, it's the vertical total electron content.
Yeah.
At every of these points, at every in this grid.
Okay.
Yes. So
But you count them this one in real time?
yeah.
Okay.
If you are inside, the region of coverage,
Yeah.
of the EGNOS, of the WACS, of any of these ESCOs, you can get the information. But also, you can get this information through internet. They are also disseminating this information by internet in real time. And also, they store all of this information in an archive, in an FTP. So you can also download the vertical text derived from SBAS for a given date. So real time from the satellites, real time from internet, or archive. You can get 3 different sources. At least, maybe there are more, but I think at least there are 3.
And slide 15, you present one map about the availability of the
50?
yeah this one the top tier availability. How I count them this one for one position mode? It's for example, I propose this one. We have calcs or methods that I can apply to understand and obtain this map, or it's about you test and understand.
Well, for these maps, you can also use a GLab to compute these maps.
Okay.
So what these maps tell us, how we derive these maps, is for every region, so you start maybe at Madrid, the center of the Iberian Peninsula. And here it's like you place a perfect receiver, what we say a fault-free receiver. And then we check the availability here, and then we move 1 degree to the west, and then to the west, to the east, and then we complete the map one by one. In every of these points, what we use is the navigation message and the SBUS correction. We are not using a real measurement from let's say a station. We only are testing the messages. This is why we say that it's a fault-free receiver. So we are testing basically the geometry, so we screen all of the geometry, and we are testing the content of the messages. But this, if you have the broadcast navigation message and the SBUS corrections, you can use the GLab to compute these maps.
That's it.
Okay. Yes?
I have a question. Was there in the implementation of EGNOS, do you know if ECAUS intends to decrease the minimum separation between aircrafts, at least on the European continent? Or
I honestly don't know what are the plans of ICAO. I don't know. Maybe you can write to Javier from ENAIRE that they are more close.
Okay.
They are following all of these international panels and so on. Maybe he knows a little bit more where ICAO is going. And then not to me, sorry.
my father is ATC, works on ATC, so he would be quite interested in this.
Sure. Sure. Then try with Javier.
Okay, thank you.
Okay, so if there is no more questions here in the room and on the meet, then we can finish here for today's lecture, and we then go for the coffee break, and we continue with the laboratory. So, thank you very much.